Guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, we're going to look at an interesting part of the application of the radius of gyration, and we're going to use some of the concepts which we have learned in some of our previous videos on the concept of the moment of inertia and radius of gyration, in trying to show that basically the radius of gyration for, of course, a uniform rod of length given as S, rotating along its end is given as 0.577 s. So in this case, we are going to use some of the discussions which we have made in our previous videos, and therefore we can evaluate and show that basically this is going to be true by considering the moment of inertia of an infinitesimal particle of this specific rod in terms of this specific representation. So we are going to have the sigma I representing the moment of inertia of an infinitesimal particle of this specific rod given in terms of sigma m, the square of x, given as that one. So in this case, we're going to consider this one, of course, as the moment of inertia given as that one. So in this case, we had said that we can represent this aspect of mass by considering it as a product of various entities. So we're going to have this, of course, sigma m represented in terms of rho a dx, and of course, that is going to be multiplied with the square of this specific aspect of x squared given as such. So in this case, this is going to be representing our sigma m. And of course, we are going to be utilizing such a kind of approach as we proceed. So we're going to consider this one in the limit as this particular aspect of sigma x tends to a small unit. So we're going to have this one as sigma x. So as this one tends to be small and smaller, we're going to consider that specific limit, and therefore that's going to require us to use a differential which is going to be given as a dx, and that is going to assist us to an integration in order for us to find the total moment of inertia of this specific, of course, rod that is rotating at its end. Now, from the concept of the moment of inertia, then therefore we can find the radius of gyration from our previous discussion which we have done. So therefore we're going to have this one given in terms of those specific differential dx, and therefore we are going to be performing our integration, whereby we are going to have this one given as the integral. So the total moment of inertia will be given as the integral between 0 and the x, as 0 and the s, as we have said. This is going to perform to be, of course, the total length. And of course, we are going to have this one as the product of density times area times the square of x dx, which is our differential that I've just mentioned in my previous statement. And of course, we are going to consider taking this one rho a out, which are going to be forming our constant. And therefore, we shall evaluate the integral between 0 and s of this value of x squared dx given as that one. So this is going to be giving us the value of rho a, and of course we shall have this x all over 3. So this is going to be x cubed for an integral all over 3 from the value of 0 to s given as that one. And of course, if we do a further evaluation, this is going to be giving us a third rho a, and then we shall have s to power 3 as our moment of inertia. And from this one, we are going to consider this specific aspect of what we refer to as mass. Remember, in our previous representation of the concept of a moment of inertia, we are going to use the aspect of mass. And in our calculations or normal evaluations, we know that this is going to be density. And of course, the cross-sectional area times the length of this specific aspect is going to be giving us what we refer to as volume. Now, the product of a mass density times volume is going to be giving us a mass. And in this case, we're going to look for a section of these specific variables, which is going to be a density area. And of course, one of the s is going to be forming our mass. So therefore, we can transform this specific representation for the moment of inertia given in terms of a third ms squared, whereby one of the s is going to be catering for these variables which are going to be forming this aspect of a mass. But we had decided in our introduction to the radius of gyration that we can find the moment of inertia given in terms of the product of the radius of the square of the radius of gyration and mass, and therefore we can equate this to a specific formula in order for us to find the representation for the value of a k. So in this case, we are going to have a third ms squared is equivalent to mk squared. So in this case, the common factors are going to cancel out, and therefore we're going to have the square of k given in terms of a third s squared given as that one. Thereafter giving us a k equivalent to, of course, s over the root of 3 given as such. So in doing our evaluation for that one, this is going to be giving us the value of k as 0.577 s given as that one. And that is going to be our proof that basically for a rod that is rotating along its end with a length of s, its radius of gyration can be given in terms of these specific values. So kindly check our description boxes for various links of other videos. Subscribe and engage us in the comment section, and also ring that notification bell for various updates on different topics in mathematics and sciences. So that is it for now, guys. Bye, God bless. We'll catch us in our next video.